Hello guys, welcome on Tesla Adventures. In this video, we are discussing the type 2 problems, in fact type 4 problems which are based on pistons, but this is the part 2 of piston problems. So in this first question you can see that there is a cylinder which has a non-conducting walls as well as a non-conducting piston. This piston A is movable and it is non-conducting, as well as the volume of argon and hydrogen initially in both the chambers is same, which is equal to V naught. And in the first part it is given that piston B is also non-conducting, and this piston A is pushed downwards slowly till the volume occupied by the argon becomes V naught by 4. So we have to find out the volume occupied by hydrogen after compressing the argon. Now first of all, let us see that as there is no heat exchange of any gas with the surrounding or any gas with each other, so there is a adiabatic process for both of them. And in adiabatic process, let us suppose that initial pressure was P naught, the atmospheric pressure, and for argon, if I use P1 V1 to the power gamma is equal to P2 V2 to the power gamma. So for argon, you can see that argon is a monoatomic gas, so initial pressure was P naught, volume was V naught, and for gamma is equal to 1 plus 2 by F, where F is the degree of freedom, and for argon degree of freedom is 3. So gamma for argon will be equal to 5 by 3. So this is 5 by 3, and P2 is the pressure of the argon finally, and V2 is the volume, and the volume occupied by the argon finally becomes V naught by 4. So it is V naught upon 4 to the power 5 by 3. So P will be equal to 4 to the power 5 by 3 into P naught. This is the pressure of this gas, final pressure of the argon gas. Now let us also discuss about the hydrogen gas. So for H2 gas, this process is also adiabatic. So P1 V1 to the power gamma is equal to P2 V2 to the power gamma. Now initial pressure of hydrogen was also P naught and volume was also V naught, but for hydrogen gamma will be degree of freedom will be 5 and gamma will be 5 by, in fact 7 by 5. Okay, so P naught V naught to the power 7 by 5 is equal to final pressure of argon and hydrogen will be same, because this piston is movable and the gases are in equilibrium. So final pressure of the hydrogen will be 4 to the power 5 by 3 of P naught, and the volume of that hydrogen is V, so it is 7 by V to the power 7 by 5. So V will be equal to V naught divided by 4 to the power 25 by 21. So this is the final volume of hydrogen gas. Now in the B part we have to now we have to assume that the piston B is conducting, and each gas has n number of moles, and some external agent performs a work done of W naught in slowly pushing down the piston A, and we have to find out the rise of temperature of each gas. So we can see that if the middle piston B is conducting, then these gases will share the heat isothermally, which means that in fact the temperature of these two gases will be same at all the time. I am not saying that it is an isothermal process, but I can say that temperature of the gas, both the gases at any instant of time will be same. So if their temperature is same, then we can say that delta T will also be same, because initial temperature and initial pressure volume was same. So we can say that for system work done on system is equal to W naught, and work done by system is equal to minus W naught. Heat exchanged by system is 0 because these two gases are filled in adiabatic cylinder, which does not allow any heat exchange with the surroundings, but these gases can exchange the heat between them. But when I am considering them as a system, then I can say that the complete heat exchange of the system with surrounding will be 0. So for the complete system, we can apply delta Q is equal to du plus dw, and du will be equal to minus of dw, and du will be equal to plus w naught because dw is minus w naught, and du will be du1 plus du2, that is equal to w naught. Now number of moles are same, n, and for the argon Cv is 3 by 2 r delta T, and for that hydrogen gas it is 5 by 2 r delta T, and that would be equal to W naught. We can easily assume that the temperature change of the gases will be same, because finally when the equilibrium will reach, the heat exchange between the gases will be ceased, and therefore the gases will be in thermal equilibrium at all the point of time. So I can say that this is 5 by 2 plus 3 by 2, that is 4 nr delta T is equal to W naught, and delta T will be equal to W naught upon 4 nr. So this is the rise in temperature of each gas. Now we move on the next question. In this question, you can see that there is an arrangement as shown in the figure. This piston can smoothly move inside the cylinder, and mass of the piston is 100 grams. The cross-sectional area of the piston is 10 centimeter square, and the initial length column is 10 centimeter, this one. Now the temperature of the air initially was 27 degrees Celsius, and the overall length of the cylinder is 20.4 centimeters. Now this container is turned upside down, and the length of the air column now becomes L, temperature remaining same. Now we have to find out that what is the new length of the air column, assuming that air is a diatomic gas. Now we know that initially the pressure acting from the top is P naught, and pressure of the air is P. So P will be balancing out P naught plus mg upon area. So P initially P1 is P naught, which is 1.01 into 10 raised to power 5 plus mg upon area. Now mg is equal to 1, and area is 10 to the power 3. So P1 is equal to 101 into 10 raised to power 3 plus 10 raised to power 3. So this is 102 into 10 raised to power 3. This is P1. And P2, when we turn down this cylinder like that, then obviously this piston descended down, and the new length of the air column becomes L, and now the pressure becomes P2, and atmospheric pressure is still P naught. So P2 will be equal to P naught plus mg upon area. In fact, P naught minus mg upon area. So P2 will be equal to 101 into 10 raised to power 3 minus 10 raised to power 3, which is equal to 100 into 10 raised to power 3. So it is 10 raised to power 5. And now we can use P1 V1 is equal to P2 V2, and as you know that the area of cross section of the cylinder is constant, so what we can do is the fact that P1 L1 is equal to P2 L2. Now P1 is 102 into 10 raised to power 3, L1 is equal to 10, and P2 is 10 raised to power 5, and L2 is equal to L. So L will be equal to 10.0, 10.2, you can see. So this is the length of the air column finally. Now we move on the next question. In this problem, you can see that there is a ball of radius r that is tightly fitted inside a tube that is attached to a container. This container contains air of volume V0, and there is no friction between the walls of the tube and the ball. The radius of ball is r, and the density of the material of the ball is d. The atmospheric pressure outside the vessel is P0, and if this ball is displaced, initially this ball is in equilibrium position. So if this ball is displaced slightly inside or outside, this ball starts to perform SHM. We have to assume that the temperature of the gas does not changes inside the vessel due to displacement of the ball, and we have to find out the time period of SHM of the ball. Now you can first of all see that this process is a isothermal process because temperature remains constant. So PV is equal to constant. PV is equal to constant, and we can say that P delta V, P dV plus V dP is 0. So dP will be equal to minus of P dV by V, and dP is the change in pressure due to the displacement of the ball. And as the ball will be displaced, let's suppose ball is displaced inside by a distance of x. So this ball compresses the air inside the vessel, and the pressure of the air becomes higher than the initial pressure, and therefore air applies a pushing force on the ball, due to which that ball performs SHM. So the pushing force dF will be equal to dP into additional due to dP into the area. Area is pi r square. The area of this tube is pi r square. So dF will be equal to dP into pi r square, and dP is minus P. P is P0 initially, and V is V0, and dV is the change in volume. So change in volume will be equal to pi r square into displacement. You can imagine that the change in volume will be the volume of this cylinder. Okay, so into pi r square also. So dF magnitude will be equal to P0 upon V0 into x into pi r square to the power 2, and this extra force is responsible for SHM of the ball, and therefore it is equal to m omega square x. Now m of the ball will be density. Now let us use the next page. So m omega square x, one second, m omega square x will be equal to P0 by V0 into x. This is P0 by V0 into x into pi square r to the power 4. So m mass of the ball is not given, but its density is given. So mass will be density into 4 by 3 pi r cube into omega square into x, and that is equal to P0 by V0 into x into pi square r to the power 4. So cancelling this r cube with this and pi with pi, x with x, and omega square will be equal to 3 p naught by 4 v naught d pi and into r, and omega will be the root of this, and omega is equal to 2 pi by t. So time period will be equal to 2 pi under root of 4 v naught d by 3 p naught pi r. This would be the time period of SHM of the ball. Now we move on the next question. In this question, you can see that there is a container that has a tightly fitted movable piston which can slide without friction inside this container, and this piston is connected with a spring that is compressed in this state, and on the left side of the container there is vacuum, and on the right side there is a ideal diatomic gas whose current, pressure, volume and temperature is P0, V0 and T0. Now it is given that if we evacuate this side of the container, if we release all the gas filled inside it, and if we create the vacuum, then this piston is found at this position. It strikes this wall, and the spring in that case would be relaxed. So we have to find out the heat capacity of the system, and we have to neglect the heat capacity of the container, piston and the material of spring. Now we can easily imagine that if there was vacuum in this chamber, then spring was relaxed, and now in this case spring is compressed by a distance of x, and we can say that P0 into area will be equal to kx. So the value of k will be equal to P0 a by x, and the energy stored in the spring is half k x square. So U will be half k is P0 a by x, and x square is this. So U will be equal to half P0 a into x. Now we can also find out the value of x by the concept that initially when the piston was at this wall, the volume of the gas was 0, and now the volume of the gas is V0. So the change in volume is V0, and change in volume will be equal to x into area. So x will be equal to V0 upon area. So the value of U will be equal to half P0 a into V0 upon area. Cancelling a with a, U is equal to half P0 V0. This is the energy stored in the spring, and we also know that initial temperature of the gas can be regarded as 0 when there was vacuum, and the final temperature is T0. So we can say that delta U will be equal to N CV delta T. And CV is diatomic gas. For diatomic gas, CV is equal to 5 by 2 R. So it is N into 5 by 2 R, and delta T is T0. Now NR T0 is P0 V0. So it is 5 by 2 R, in fact 5 by 2 P0 V0. This is delta U. And we can see that the heat supplied can be written as dq. Let us use another ink. Yeah, heat supplied can be written as du plus dw. Now dw is the work done against spring, which is half kx square, and we have already calculated the value of kx. So the value of half kx square is this one, half P0 V0. So it is half P0 V0, and du is 5 by 2 P0 V0. du is 5 by 2 P0 V0. Now the heat supplied to the gas is du plus dw, and that is 3 P0 V0, and dq can be regarded as heat capacity into delta T. and obviously heat capacity H will be equal to 3 P naught V naught upon delta T, which is T naught. So this will be the heat capacity of the gas. Now we move on the next question. In this question you can see that there is a freely sliding massive piston which has a high amount of mass, is supported by a spring as shown in the figure, and when all the air is pumped out from the container, then piston remains in equilibrium with only a tiny gap between the piston and the bottom surface of the cylinder, which means that in this position, in equilibrium position, this piston is not exactly touching the bottom of the cylinder. There is a tiny air gap, which means that this spring Kx is balancing this mg of the piston. We can assume that the natural length of the spring is 0. It is just an assumption because the solution will not depend on the natural length, so we can assume that the natural length is 0, and the extension in this state is x0, so kx0 is balancing out mg. This is the first case. Now when some gas is pumped between the gap, then piston moves in the upward direction, and therefore now final extension at this position in the equilibrium will be x0 minus h0. So we can balance the forces. We can say that F of the spring would be acting in the upward direction, pressure is P1, and mg is acting in the downward direction. So F plus P1A will be equal to mg, and F will be equal to k x0 minus h0. So k x0 minus k h0 plus P1A is equal to mg, and cancelling this mg with k x0 by this equation, k h0 is equal to P1A, first equation. Now let us in the second part, what we have done is the fact that we have increased the temperature of this gas from T0 to 4 T0. Now this piston will move further in the upward direction, and let's suppose that final height in final equilibrium is h. So again, by this analysis we can directly say that kh will be equal to P2 into area. That is the final pressure of the gas. So P2 by P1 will be equal to h by h0, and the other equation is the fact that you can see that initial pressure of the gas was T0, and finally the initial temperature of the gas was T0, and final temperature is 4 T0, but number of moles remains the same. So we are equating P1 V1 upon T1 is equal to P2 V2 upon T2. So the P1 pressure was P1, and volume was initially in this state was H0 into area, and temperature was T0, and finally pressure is P2, volume is H into area, and temperature is 4 T0. So you can see that P2 by P1 from this equation is equal to H0 by H into 4, and we can equate these two equations, and we can say that H by H0 will be equal to 4 H0 by H, 4 H0 by H. So H square by H0 square will be equal to 4, and H will be equal to 2 H0. So this will be the final height of the gas in the cylinder. Now we move on the next question. In this problem you can see that there is a spring which is connected to a massless lid of a container, and initially this lid is held in this position by this spring, and a spring is applying a force of 1000 Newton in the downward direction, obviously, to keep this lid in this position, because the pressure of the gas inside the vessel is P0 and pressure of the gas outside the vessel is also P0. Therefore, to keep this lid on the top of the vessel, this spring has to apply a force of 1000 Newton in the downward direction. Now obviously we can say that the spring force per unit area, F upon area, is 1000 upon 10 to the power minus 2. Area is 100 centimeter square, so it is 10 to the power 5. So actually spring is applying a pressure of 10 to the power 5 pascals on the lid in the downward direction. Now we have to heat this gas initially, which was at the temperature of 300 Kelvin, to such a temperature such that this lid just takes off and the gas starts to escape out. So we can say that the final temperature of the gas should be equal to 2 P naught, because it would balance the P naught pressure of atmosphere as well as it would balance the P naught pressure of the spring. So if the pressure of the gas is 2 P naught in the upward direction, then the net force on the lid would become 0, and lid will start to rise up and the gas will start to escape from the vessel. So the final pressure should be 2 P naught, and we can see that volume is constant throughout this heating process. So temperature will be also double of the initial temperature. So temperature would be 600 Kelvin, and the heat supplied at constant volume is NCV delta T. Now N is 2 moles is given, and CV for monoatomic gas is 3 by 2 R, and delta T is 600 minus 300, which is 300. So this is 900 R. So heat required to be given to the gas is 900 R. Now we move on the next question. In this problem you can see that there is a ball of radius R that is tightly fitted inside a tube that is attached to a container. This container contains air of volume V0, and there is no friction between the walls of the tube and the ball. The radius of ball is R, and the density of the material of the ball is D. The atmospheric pressure outside the vessel is P0, and if this ball is displaced, initially this ball is in equilibrium position. So if this ball is displaced slightly inside or outside, this ball starts to perform SHM. We have to assume that the temperature of the gas does not changes inside the vessel due to displacement of the ball, and we have to find out the time period of SHM of the ball. Now you can first of all see that this process is a isothermal process because temperature remains constant. So PV is equal to constant. PV is equal to constant, and we can say that P delta V, P dV plus V dP is 0. So dP will be equal to minus of P dV by V, and dP is the change in pressure due to the displacement of the ball. And as the ball will be displaced, let's suppose ball is displaced inside by a distance of x. So this ball compresses the air inside the vessel, and the pressure of the air becomes higher than the initial pressure, and therefore air applies a pushing force on the ball, due to which that ball performs SHM. So the pushing force dF will be equal to dP into additional due to dP into the area. Area is pi r square. The area of this tube is pi r square. So dF will be equal to dP into pi r square, and dP is minus P. P is P naught initially, and V is V naught, and dV is the change in volume. So change in volume will be equal to pi r square into displacement. You can imagine that the change in volume will be the volume of this cylinder. Okay, so into pi r square also. So dF magnitude will be equal to df will be equal to p naught upon v naught into x into pi r square to the power 2, and this extra force is responsible for SHF of the ball, and therefore it is equal to m omega square x. Now m of the ball will be density. Now let us use the next page. So m omega square x, one second, m omega square x will be equal to p naught by v naught into x. This is p naught by v naught into x into pi square r to the power 4. So m mass of the ball is not given, but its density is given. So mass will be density into 4 by 3 pi r cube into omega square into x, and that is equal to p naught by v naught into x into pi square r to the power 4. So cancelling this r cube with this, and pi with pi, x with x, and omega square will be equal to 3 p naught by 4 v naught d pi and into r, and omega will be the root of this, and omega is equal to 2 pi by t. So time period will be equal to 2 pi under root of 4 v naught d by 3 p naught pi r. This would be the time period of SHM of the ball. Now we move on the next question. In this question, you can see that there is a cylinder which is of bottled shape, and there are two pistons A1 and A2. The area of this piston is A1, the area of this piston is A2. Masses are M1 and M2. It is given that the sum of the masses of these two pistons M1 plus M2 is equal to 5 kilogram, and the difference of area of the two pistons A1 minus A2 is 10 centimeter square. If this gas is heated slowly, then this piston system rises up by a distance of 50 centimeter. They are being connected by a thread, and we have to find out the rise in the temperature of the gas. Now we know that the atmospheric pressure will be acting in the downward direction P naught, and on this piston it would be acting in the upward direction. So the work done by gas will be equal to mgh as well as work done against atmosphere, against PATM. Now let us find out the work done against atmosphere. We can see that work done against atmosphere PATM is equal to, you can see that the net opposing force of atmosphere will be P naught into A1 minus P naught into A2, due to the fact that this upper air is opposing this piston to move up and the lower air is supporting the piston to move up. So the net work done will be force into displacement, which is H. So this is P naught H into A1 minus A2. Now let us sum up these two work done. So net work done by the gas will be mgh. Mg is 50, H is 0.5 centimeter, 0.5 meter, plus P naught into A1 minus A2 is 10 into 10 raised to power minus 4 into H. H is again 0.5. So work done will be, this is 25 plus this will be 10 to the power 5 into 10 to the power minus 3 into 1 by 2. So you can see that this is 50. So the total work done is 75. So the total work done by the gas is 75, and pressure is constant in this process because pistons are moving slowly, and the pressure of the gas and the pressure of the surroundings and mg of the piston is constant. So at all the time, the net force acted by the gas on the surroundings will be equal and will be zero on the system. So we can say that pressure of the gas will remain constant, and therefore the work done will be equal to P delta V. So work done is 75 and P is P naught, and we can say that P delta V is also equal to NR delta T. So the number of moles, I think it is given in the question. One mole, yeah, it is given as 1 mole, and N is equal to 1. And we can also see that work done is 75, N is 1, R is 25 by 3, and delta T is the rise in temperature. So delta T will be equal to X by R Kelvin. So we have to find out the values in terms of R only. So let us substitute the value of R as R. So delta T will be 75 by R. So the value of X will be 75. Thank you.